So first of all, I'd like to thank organizers, Takayanagi-san and Ugajin-san, for giving an opportunity of this talk in this great workshop. So at first, I tried to talk about all my recent paper on the quantum computation and also tensor network, but the tensor network paper does not yet submit on archive. So mainly today, I'd like to talk about this paper on the quantum computation analysis on the Schwinger model. So, and let me start a brief introduction myself. I'm Etsuko Ito, a senior research scientist in ITEMS, Riken. So ITEMS stand for the interdisciplinary theoretical and mathematical science. So it has roughly 100 theoretical scientists and mathematicians, including the physicists and biologists, information theorists, and so on. So, and I am also member in the 01 group of this Extreme Universe project. So the D stands for the dynamics of quantum matter, and the color is purple. So, and so in this talk, I'd like to talk about the dynamics of fundamental matter. And yeah, actually, originally, I have been working on the numerical study of quantum field theory, in particular Lattice QCD, using the classical supercomputer. And very recently, I started my work on the quantum computation. So in this talk, I'd like to talk about the what dynamics I want to understand and why I am excited about the quantum computation recently. So this is the outline of my talk based on my research background. So I will first introduce my research target, QCD. So, and I'd like to briefly introduce several success of the Lattice QCD to date. And then I will explain my motivation why quantum computation is needed instead of the conventional Lattice QCD method. And as an example, we demonstrate the quantum computation on the Schwinger model. And actually, we perform the demonstration on the extended Schwinger model. So, and actually, I'd like to explain this picture. So why this smart cat is surprising on the our simulation result. So this is the bottom line of my talk. Okay. Actually, and this picture is drawn by Masazumi Honda, my collaborator, for the press release of our paper. Okay, so let me start. What is QCD? The starting point is the atom for the broad audience with different background. So you know, so atom has a hard core in center, nucleus, and as you know, nucleus consists of protons and neutrons. And if there is only electromagnetic force, then proton has a repulsive force, and the neutron does not have electric force. So nucleus does not form. So because, and actually there is a stronger force rather than the electric force in the nucleus, and it binds the proton and neutron. And the QCD is a microscopic theory of this strong force. And it is described by a 3+1 dimensional SU3 gauge theory coupled to the fermion, so-called quarks, and the gauge field is called gluons. And so to understand the phenomena of this strong interaction, so you know, perturbative analysis is not valid anymore. So we need some non-perturbative method and actually numerical calculation. And the method is the Lattice Monte Carlo QCD. And lattice Monte Carlo QCD reveals the hadron physics from QCD action. Okay. And yeah, actually, one of the characteristic property of QCD is confinement. I think you know. So we cannot pick single quarks from the nucleus. And actually, this is the quark anti-quark potential obtained by lattice numerical simulation. So the potential shows that in short range is a Coulomb potential, and in long range it has a linear potential. Okay, so because of the linear potential, so if we put a single quark apart from the another quark, so we need much energy. This is a signal of confinement. And in fact, the first study of the lattice QCD has been done by the Mike Kreutz in 1980, and he shows the string tension, this coefficient, using the lattice Monte Carlo simulation for the SU2 gauge theory. At that time, lattice size is 10 to the fourth. So anyway, showing the confinement, find the linear potential is beginning of the lattice QCD. And for this 40 years, lattice QCD has many successes. So for instance, this is a famous plot of the hadron spectrum, the composite state of the quarks. So proton and neutron and kaon and pion and so on. So this red data is obtained by the lattice Monte Carlo simulation. Actually, Aoki-san and Tsukuba University group. And black data shows the experimental data. So you see perfectly excellent consistency between the experimental data and lattice theoretical result. And recently, we can find the nuclear force. The previous plot is a quark anti-quark potential, but we can obtain the nucleus potential. So this is given by the Aoki-san, Ishii-san, Hatsuda-san, and HAL-QCD collaboration. So from this potential shape, so we can understand why the nucleus never collapse. Because in short range, there is a repulsive core. And around the 1 femtometer, there is a attractive force pocket. So this 1 femtometer indicates the size of nucleus. Okay. And furthermore, in the lattice QCD calculation, using the imaginary time formula, we can investigate the finite density, finite temperature system. And this is a plot of the thermodynamic quantity, thermal entropy, and internal energy as a function of temperature. And these lattice results give an input of the evolution of the early universe, hot early universe. So, and surprisingly, so, QCD has 3 or 4 input parameter. So QCD has a gauge coupling constant and UD quark mass and strange quark mass. That is all we can choose a parameter. So, but within the few input parameter, these lattice QCD explain the rich QCD non-perturbative phenomena. This is great. And furthermore, actually, this is a surprising plot shown by the Lena Funke in MIT at the Lattice International Conference this year. So yeah, actually, I'd like to say here, lattice QCD theorists are relevant user of supercomputer. So this is a pie chart of the supercomputer usage of different fields. So there is astrophysics, biophysics, and material science, and nuclear physics, weather, and climate. But lattice QCD has a roughly 40% share in this pie chart. So I strongly believe in the fault-tolerant quantum computer error. We will be a heaviest user of the quantum devices. And but anyway, so however, you know, some lattice QCD theories are attracted by the recent quantum computation and tensor network. So next, I'd like to explain why quantum computation, although we have a great lattice QCD method. Okay, and the answer is simple because of there is a infamous sign problem in some case. So to explain the my motivation in detail, so let me start very elementary things. So what is lattice Monte Carlo QCD? So actually, generally speaking, we would like to know the expectation value of physical observable O. And using in the lattice Monte Carlo simulation, we calculate this quantity based on the Euclidean passive integral formula. So, and this O is, for instance, chiral condensate or Wilson loop or a correlation function of some composite state. And so to explain what is lattice Monte Carlo QCD, so let me start what is Monte Carlo algorithm. So this is a simple example. Let me consider this simple integral. So as you know, you can find that this is the area of this fan shape, radius equal 1. So to obtain this integral, the answer in the Monte Carlo simulation, we generate the two sets of random number in the interval 0 to 1. And we named these two random number x and y and plot in this two-dimensional plane. And we count the number of dots inside this fan shape. And it denotes the Sn. And we also have the total number of trial n. Then taking a ratio Sn and this total n, and taking n goes to infinity limit, then we obtain the area of this fan shape. And so in the simple case, we can use the differentiation of the product method, 구분Q積法. But in the case of a multidimensional integral, lattice Monte Carlo is a faster algorithm than this 구분Q積法. So if we can generate the random number fast using the fast algorithm. And actually, in our lattice Monte Carlo simulation, yeah, actually I continue the work on the using the supercomputer Fugaku. In my simulation, I have 6 billion degree of freedom of this integration. So we need a fast algorithm. And in the previous example, I generate the uniform random number, but honestly speaking, the usage of the uniform random number is inefficient. And in the quantum system, you know, the classical configuration is favored. So to generate the configuration efficiently, we use the exponential of minus Euclidean action as a Boltzmann factor. So it is called the importance sampling method. So we use this factor as a probability weight for each configuration phi. But in this method, we use this factor as a probability weight. So this Euclidean action should be real and positive. But if we consider gauge theory or QCD in finite density region, or if we consider gauge theory at the topological theta term, or consider the real-time evolution of QCD, this Euclidean action takes complex number. So probability weight interpretation is not valid anymore. And actually, obtain the answer of this integral, we need the infinite number of sampling. However, this setup of the gauge theory of QCD is extremely important. For instance, in the case of the finite density QCD, this is a famous plot of the QCD phase diagram, temperature and density. The conventional lattice Monte Carlo is valid only at this axis, finite temperature at zero density region. But here, there is an important matter, so-called neutron star. So in low temperature and high density region, there is a neutron star. It consists of the neutron, roughly 95%. So we believe it is definitely QCD matter. So in principle, we can obtain the phenomenology of the neutron star from the QCD action. This is a dream. And also real-time evolution of QCD is directly related with collider physics. This is a movie given by the Riken. And so to investigate what is happening in collider, we need the theoretical prediction using the some method. But the this is a motivation. So this first principle calculation has been desired for a long time. And so one of promising alternative method is a calculation based on the Hamiltonian formalism. As I explained it, conventional lattice Monte Carlo QCD is based on the Lagrangian formalism in Euclidean space-time, but our real world is in the Minkowski space-time. And if we consider the quantum field theory in the Hamiltonian formalism, sign problem is absent at the beginning. This is a great motivation why we focus on the quantum computation and the recent tensor network. But of course, we have several problems we have to solve. The severe problem is here for our high energy theories. So as I explained it, so quantum computation based on the Hamiltonian formalism, implementation of the fermion field is rather easy. However, the implementation of the gauge field is difficult because even if consider only the physical degree of freedom gauge field, it has essentially infinite dimensional Hilbert space. So we need some good regularization method, but it is still unknown for non-abelian gauge theory or in higher dimensional gauge theory. And so at the present, there are two directions. First one is introduce some cutoff of Hilbert space, but it breaks some gauge invariance explicitly. And the other direction is we change the gauge symmetry and from SUN to some discrete symmetry. So this is a situation. And I'm not sure, but to obtain some hints to find the regularization method, again, let me remind what is happening in the conventional lattice QCD method. So in conventional lattice QCD method, fermion field is all fermion degree of freedom are integrated out because unfortunately, QCD has only bilinear term of the fermion field. So we can exactly perform the Gauss integral. And in the Lagrangian formalism, gauge invariance is manifest by introducing the unphysical degree of freedom of the gauge field. And I think this is the breakthrough point given by the Ken Wilson. So gauge field is expressed by the compact representation, so-called link variable. So the gauge field itself has takes a value from minus infinity to plus infinity. But in actual our calculation, we utilize this compact representation, the magnitude of this atmosphere unity. So yeah, this is the situation, but I don't have answer for the good regularization method in the Hamiltonian formalism. So honestly speaking, we are waiting for the post-Ken-Wilson for the quantum devices. But I'd like to share this open problem. And so this is the current status. And so in the conventional method, we have a sign problem and quantum computation for non-abelian gauge theory or higher dimensional gauge theory suffer from the several problems. But fortunately, we have one gauge theory model, so-called Schwinger model. So I will explain later, but for the Schwinger model, we don't need any truncation or approximation. And we can demonstrate the Schwinger model in Hamiltonian formalism with this setup can be performed by using the quantum algorithm. And actually in this talk, I will show you our demonstration for the Schwinger model with topological theta term. And before showing our result, I must mention about the general problem of the quantum computer. As you know, the current device, quantum devices, is has a small qubit size and suffer from the quantum error. And actually, this is a schematic picture of picture. And the horizontal axis is the number of qubits, and vertical axis is the number of qubits, and the horizontal axis gate operation accuracy. Current devices is around here. Size is 10 to 100, and gate operation is 0.01 to 0.001. And the current devices touch the region of quantum supremacy. Actually, Google has been done in 3 years ago. But the problem people want to know, people want to solve around here. So we are waiting for the development of real quantum devices. So our work, actually our result is obtained by using the Qiskit simulator. And this is essentially using the classical computer, but we use the quantum algorithm to find the feasibility test of our strategy. So that is an overview of the our work. And so do you have any questions so far? Is it clear?
Is it clear how the sign problem is actually related to the problems that occur in the Hamiltonian formalism? Do we understand how they map to each other?
Yeah, actually, even in the Hamiltonian formalism, in some case, we have a sign problem. So yeah. Okay. So now let's move on to the specific model, so-called Schwinger model. This is actually 1+1 dimensional quantum electromagnetic dynamics. And yeah, here I'd like to explain the Schwinger model is a very good toy model of QCD. So QCD, as I explained it, so this is given by the 3+1 dimensional SU3 gauge theory coupled to fermion, so-called quarks. And Schwinger model is 1+1 dimension U1 gauge theory coupled with fermion, so-called electron. So you find, you understand that this is just a reduced model, dimensionality and the gauge symmetry of the QCD. And here we would like to consider the potential between the two probe charge QP and minus QP. and the distance is L. And in the standard case, so if the charge is an integer, integer means the unit is E, so electric charge. So in the standard case, integer probe charge, this model has a screening potential like here. So in the long distance, the potential has a plateau because string is breaking by dynamical pair creation of the particle and the antiparticle. However, theoretically, we can consider in the case of the fractional charge, probe charge. So in this case, so dynamical pair creation does not occur because dynamical fermion has the integer charge. So then the string between particle and the antiparticle stretches in the long distance. So the potential getting larger, and it shows a linear potential as like the QCD. And furthermore, here we would like to add the theta term to the Schwinger model. So this is a Lagrangian of the Schwinger model, and we add this term, theta term. And in the non-zero theta region, in the conventional method, a sign problem appear. And this is one plot obtained by the Monte Carlo simulation for two-flavor Schwinger model given by the Fukaya-san and Onogi-san. So they investigate the hadron spectrum pi on Mars as a function of theta, and you see the statistical error almost diverge in the large theta region. This is a signal of the sign problem. And our strategy will utilize the Hamiltonian formalism to obtain the Hamiltonian. The goal is Hamiltonian expressed by the spin variable. And to do that, there are several steps. But anyway, we introduce a gauge fixing and solve the Gauss law constraint and impose the open boundary condition. Then the Hamiltonian is given by the only fermion field. And in this process, we don't have we don't use any truncation or approximation. And finally, using the Jordan-Wigner transformation, we obtain the Hamiltonian expressed by the spin variable x and y and z. This is a Pauli operator. And so the first term is a kinetic term of the electric field. Basically it comes from this F mu term. And the second and third term describes the kinetic term and the mass term of electrons. And here is a theta term. So in this formulation, so theta is just a constant shift of electric field. So any additional difficulty comes by insertion of the theta term. So this is a Hamiltonian formalism. And some condensed matter theorists worry about this term. Actually, this term is the all-to-all interaction of GI. So, but yeah, practically we can implement this Hamiltonian and could perform the quantum computation and the tensor network simulation. And the reason come from the original Lagrangian is a local, has a local interaction. And also in the case of one flavor Schwinger model, the system is a gapped system, even in the massless fermion case. So that is why we can perform the DMRG and the actually entanglement is finite in the large volume simulation. Okay. So let me show you our result for the extended the Schwinger model, and this explains this smart cat. So here we extend the Schwinger model to the charge Q Schwinger model, and given by the Misumi-san and Tanizaki-san and Mitat Unzer 3 years ago. So just the modification is just puts the Q in this term. So, but however, this charge Q Schwinger model has an interesting behavior. In the case of this dynamical charge Q is larger than 1, and it takes actually we assume that this is a integer. Then in this case, the Hilbert space decomposes into the Q sector like that, and this K labels the sector, and it's around 0 to Q minus 1. And the most interesting behavior is the ground state energy is sector specific. So this is the ground energy of sector K. So it depends on the theta and the K. And now we would like to consider the potential between probe charges. So the charge insertion induces additional electric flux only between the probe charges. So to implement such a situation, we change this term, theta term in the Hamiltonian. So this theta is now site-dependent theta. So this is a setup of the site-dependent theta. So here I call the region between the particle antiparticle is inside Wilson loop, and the other region is outside of Wilson loop. And in the site-dependent theta takes theta not outside the Wilson loop, and inside the Poirier loop, it is shifted by the 2 pi probe charge QP probe charge. And this is a detailed simulation setup. So we utilize the IBM Qiskit library, actually simulator, not quantum devices. And in our actual simulation, we take the dynamical charge Q equals 3, and probe charge is QP equal -1. And the lattice size is 70 to 25. And impose the open boundary condition to remove the all degree of freedom of the gauge field. The number of shots is 1 million. I did too much. And the ground state is generated by the adiabatic state preparation given by this equation. And we prepare the nil state as the initial state, and using the second order Suzuki-Trotter decomposition and obtain the ground state. And the measurement observable is the Hamiltonian itself at the distance L. So eventually we will find the potential as a function L using this equation. This is the strategy. And now this is our result. So in the case of the probe charge QP divided by the dynamical charge Q is not integer, charge Q Schwinger model also shows a linear potential, but the slope depends on the value of theta. So this black data potential is in the theta equal 0, and green one is a theta equal pi, and magenta is a theta equal 2 pi. So first of all, I'd like to say, so in the large theta region, you see statistical error does not diverge. So there is no additional difficulty in the large theta region. And from this plot, you see the large theta region, linear potential has negative slope. So it is a negative string tension appear. So that is why this smart cat is surprising. So in standard case, you know, two particle with opposite sign has an attractive force. This is electromagnetic dynamics. But this linear potential with negative string tension shows it has a repulsive force. So this is a reason why.
Just a question about this.
Yes.
So earlier you had showed plots about how the sign problem affects as you move to the right side of this plot. That was for that wasn't for this model, correct? So what happens with the sign problem and the statistical error for this model?
For this model. So you mean in the conventional method?
I guess how does this simulation, maybe you'll answer this question soon, but how does this simulation with Qiskit compare to the Monte Carlo simulation and its statistical error?
Yeah, statistical error. Yeah, actually, we don't have any difference between the theta equals 0 and non-zero in the Qiskit simulation. So, yeah, actually, this is the answer. So, it is okay.
Question would be that, okay, so you first write this Schwinger Lagrangian of the Schwinger model in terms of this Ising type model and in terms of the spin degrees of freedom, and suppose that, okay, we do this, I mean that have this Monte Carlo simulation of this spin chain model. Is the model suffers from this sign problem or? Okay.
In the Monte Carlo simulation,
yeah,
it has the same problem.
okay.
So the physical observable is oscillate.
Okay.
So the signal become noisy.
I see.
Yeah.
So only this quantum, I mean, that the computation can cure this.
Yeah.
Even in this Ising model side.
Yeah, I think so.
Okay. Thanks.
May I ask a question? So actually, I couldn't understand what is number of shots there.
Number of shots in the Qiskit simulator.
Yeah. You are doing the how to say is it the kind of exact diagonalization or what are you doing here? So
I see. So I think, yeah, this is the I think the in actual our quantum computation, we utilize the Qiskit, and Qiskit using the quantum circuit, and I think the Qiskit generates some noise.
Okay. Yeah, your model intrinsically have some error to simulate some quantum.
Yes.
Okay, I got it.
Actual quantum fluctuation in the by the Qiskit simulator. But
I think it's just quantum measurement.
quantum measurement, yes.
Because you have the quantum state, but
Mhm.
to measure to calculate the expectation value, you have to calculate measurement. But each measurement just gives one number. But you have to repeat
Yes.
many measurements to get, like experiment, to get average or expectation value.
Yes.
I think,
That is correct. And
Also,
At
you
the-
can introduce noise.
at the
and
measurement process for each time, so the Qiskit generates some noise by using some noise model. Yeah, this is the situation.
Can I ask a question? So, yeah, could you go back to the previous page? So, what is H of L?
H of A. This
No,
one?
no, H of L.
H of L. This is a Hamiltonian with the distance is L. This distance.
But you have a global Hamiltonian, right?
Yes, but sorry. So yeah, global Hamiltonian, but this part is depend on the L value of L.
So by that, do you mean the local Hamiltonian?
Local Hamiltonian. No. We measure that this total Hamiltonian, but this total Hamiltonian, we have to fix the number of L. So and we.
I think this is just how to say L represent the shape of the potential here, kind of.
I see.
Yeah.
Okay.
Theta N represent the how to say the shape of
Yes.
configuration
Next to
of
the
the charge.
kink or something,
Yeah.
right?
Yes.
Yeah.
For each L, I generate the.
But I have questions. Usually, we put source with distance L and measure energy. But why this corresponding to this HL corresponding to putting source?
Yeah, actually, the source is charge, probe charge,
Yeah.
and this probe charge generates the extra electric flux.
Also, you
Yeah,
reinterpreted this
Yes.
charge as a,
So-
okay.
yeah, right.
I think this is because we just rewrite the integrate of the gauge degree of translate the gauge degree of freedom in terms of the spin language, and this represents
Mhm.
the potential represent the source, right?
Potential.
So such a how to say this kind of the sudden change of the data represent the such existence of charge, right?
Data dependent exists charge. So I don't get it.
Yeah, maybe naively,
Mhm.
since you put fermion,
Mhm.
charge appeared X or Y. But I think you transform that charge to
Yes,
the
that's right.
electric
Right.
Yeah,
field,
that's right.
so
That's right.
appeared Z.
That's right.
Yeah.
Very
That
complicated.
is correct. That is correct. Yeah.
So I have another question. Could you go to the next page? Maybe, sorry, maybe page 29, I think.
29?
Yeah. So what do you mean by the ground energy here?
Okay. So in this extended model, we have the Hilbert space for each sector, and each sector has a ground state. Different ground
For
state.
what? H? Because you know
As-
the H is a very difficult model to solve, right?
Did say this Hilbert in this small Hilbert space, we have a ground state.
But the ground state of what?
Ground state of the ground state of this Hamiltonian.
Total Hamiltonian?
Yes, total Hamiltonian.
But I thought that model is quite difficult to solve, right? That's why you want to use the quantum computation, right? Computer, right? So why can you get the ground state energy in this analytic fashion?
Here you are writing the express form of the ground state energy here, right?
Yeah.
So he's
Ah.
asking that
How to get this?
yeah, that's right. Yeah.
It's just approximation of the
Okay,
small mass
thank you.
participation. Sorry.
I have it.
Is it solvable, right? model is solvable.
No,
No?
in the massive case, no. Yeah, and actually, this is a this has a several mass collection term, and this is a prediction of the analytical so mass perturbation theory, leading order of mass perturbation theory. Okay, so
I have a
Thank you
simple
for-
question.
Yeah.
How to implement the Hamiltonian simulation on just use totalization or block encoding method?
that is a good question. So we have several ways to decompose this Hamiltonian to implement the Suzuki-Trotter decomposition. But in our case, we keep the number of fermion in our decomposition. So I mean, we put this term in the same how to say? Actually, if we divide the XX term and YY term with in the decomposition, then the fermion number will be changed. So we keep this structure. That is a way to implementation.
So you write that decomposition and implement then apply totalization and you learn
Yes.
Hamiltonian simulation.
Yeah. Explicit form I will show you later.
Oh, okay, thank you.
After this talk, I mean.
Okay.
So I'd like to explain what is happening behind of the negative string tension potential. So this is the answer. So the ground, so actually in the previous plot, we plot the kind of the ground state and total ground state energy. but sum of each side. But this is the energy at each side. So, and this is a Qiskit simulator result of n equal 25. So you see, and the shadow region is inside of Wilson loop. And you see the energy inside the Wilson loop is lower than the one of outside of Wilson loop. So total energy with long Wilson loop getting lower energy. This is a trick. And actually each value of energy is in small mass region, it is consistent with this quantity. So in this sense, so inside of Wilson loop and outside Wilson loop stay in the different sector of K in this situation. And this is a Qiskit simulator result. And now we perform the DMRG simulation, much larger lattice volume. So you can find that clearly inside the Polyakov loop has a lower energy rather than the outside Wilson loop. So this gives so longer L gives a lower total energy. So this is why the linear potential with negative string tension appear. And in behind, furthermore, there is actually one form symmetry. So the super selection rule of the GQ one form symmetry prohibit the vacuum decay. So, and the order parameter to see that this discrete symmetry is chiral condensate or scalar condensate. Actually, this is a preliminary result of the investigation of the scalar condensate as a function of site, number of site, DMRG simulation. So you see the outside Polyakov loop has a different value of the scalar condensate from the inside of Wilson loop. And in the quantum field, as a point of view of quantum field theory, massless case is most interesting. At that time, there is a mixed Toffuster anomaly between the discrete chiral symmetry and its one form symmetry. So we can clearly find the situation using the DMRG simulation. So I hope we will submit this paper soon. Okay, so let me summarize my talk. So in this talk, I explained it, the Lattice Monte Carlo QCD method has great successes only at the zero density region. And the quantum computation looks very promising for simulating the quantum field theory with sign problem in conventional method. And actually, Schwinger model is getting attention as a good testing ground of the new calculation method. So we demonstrate the simulation for the Schwinger model with large theta term using the quantum algorithm. And also it is looks promising to see some theoretical concept, higher form symmetry or Toffuster anomaly in extended model. And honestly speaking, there is so many problem or future direction we have to do. But personally, I want to know the physics of the QCD in the finite density region. This is my dream. So I'd like to know the perfect QCD phase diagram and hadron mass and hadron interaction around the neutron star region. And I would like to also implement the thermodynamic system using the quantum algorithm. And theoretically, the most important task is find the good description for the non-abelian gauge theory in higher dimension. Okay, that is all. Thank you.
Thank you very much for a beautiful talk. So any question? Thank you for very interesting talk. So actually, two questions. So it might be too naive question, but your calculation, I want to know your calculation is does correspond to the which region of the your QCD phase diagram here. So it is finite density or
No, the completely different axis.
Ah.
There is, there is additional axis, non-zero theta.
I got it.
Sorry.
Okay. Is it possible to think about the such finite density regime with
Yeah.
your calculation?
Yeah, actually, my friend Arata Yamamoto-san in University of Tokyo, already implements finite density stuff
I
in
see.
the Schwinger model. And actually, there is no additional difficulty in the Hamiltonian formalism. So,
Okay. Other question is it possible to actually I'm not so familiar with such lattice QCD, but is it possible to extend this model to the non-abelian, like a SU2 Schwinger model or something like that? So
yes, that is, many people try to do, but as I explained it, at present, we have to introduce some cutoff of Hilbert space or change the gauge symmetry to reduce.
if you if you introduce the naively the SU2 gauge field, and then is it impossible to integrate out or something to and then get this kind of spin chain model? Is it possible?
Impossible.
Impossible. Okay. It is special for U1, right?
Special.
I see. Okay, thank you.
Thank you for very interesting talk. And just curiosity is if you put QP equal 3, what is the energy distribution of the energy? It's just flat, 0?
It must be screening potential.
Have you confirmed?
No. But the previous paper with collaboration with Okuda-san and Nagano-san, we show the kind of screening potential using that.
Thank you.
Yeah.
Thank you very much for your interesting talk. And could you go to the slide where you showed your Hamiltonian or Lagrangian?
This one?
Yeah, and I'm wondering if it is interesting to add some terms like pair creation or pair annihilation, which in the spin language corresponds to something like some anisotropy in the term in XX and Y. I mean, the coefficients of XX is different from that of the YY.
This one?
Is that interesting? Because in the spin model literature, people also study such a model.
Yeah, actually, this term is come from this term, the kinetic term of the fermion. So to back to this form, so we need the uniform coefficient between them. But the finite density case, I don't know.
Yeah, but in terms of lattice fermions, the anisotropy corresponds to the term like Fn plus 1 plus Hermitian conjugate. I mean, the pair annihilation and creation between the neighboring sites.
Yes.
So in the continuum limit, I'm not sure what it is. But,
which one?
I mean, you can do the inverse Jordan-Wigner transformation and get a lattice fermion Hamiltonian, right?
Yes.
And in that discrete model, the anisotropy corresponds to the term like Fn. Let's say F is a annihilation operator of fermion, and the anisotropy corresponds to Fn plus 1 plus Hermitian conjugate. So this term means something like a pair creation and annihilation on the lattice, right?
Yes.
Yeah, my question is, if it's interesting or not. Yeah, so I'm just asking your opinion.
Okay. Yeah, as a spin model, it must be interesting. Yeah, I think so.
Can I ask a question? So could you elaborate your final slide? You talked about, I mean, recent updates. So your final slide.
Final
about,
slide.
I think talking about one form symmetry.
one form
Yeah.
symmetry.
So what this graph? So this graph also means some attractive force between
ね。
or
sorry.
Hmm.
This plot.
Sorry, repulsive force. Looks like repulsive force
No,
again. Or
no, sorry. This is the case of the massless case. So I think massless case, I think it has a screening potential. Yeah. Yeah, sorry.
So
Sorry
you-
for
you- as you write it here, so you get some extra phase. You can confirm this extra phase.
Yes,
expected
yes, yes.
From your analysis.
Yeah.
So to see that you're looking at the and probably not just energy, but you're computing this expectation value of scalar.
Yeah, yes, expectation value of scalar condensate. Yeah. Mhm. Yeah. Yeah. Yes.
Thank you for nice talk. I want to ask about a technical method in your quantum computation. You prepare the adiabatic state algorithm, so it means you start from very trivial Hamiltonian
Yes,
and you modify it to the final spin models.
yes,
I see. Thank you.
yes. Yeah, actually, we start the nil state as a initial state. So this is a free theory, massive free theory. Yeah. And I change the parameter in the Hamiltonian.
So my question would be that, okay, so did you say that this Qiskit simulator has already implemented this the typical error that happens in the quantum computer?
Yes.
Okay, so in that sense, I mean, okay, so this calculation is robust against these errors, and you don't need the quantum error corrections to get that. Okay, I see.
Right,
Thanks.
right. Yeah, actually, this is it has a very deep circuit. So in real devices, it is much difficult.
Yeah, thank you for the nice talk. And so I have a question about the Jordan-Wigner transform. Charge Q-bart.
Charge Q version. This one.
Yeah. So first, what is the boundary condition?
It
for-
also open boundary
Open.
condition.
Is it possible to consider the periodic boundary?
Yes, it's possible, but in the case of periodic boundary condition, the constant mode of the gauge field remains. So to implement the constant, constant takes a value minus infinity to infinity. So we need some truncation. Yeah, only this setup we can exactly implement the gauge field.
I see. And yeah, and in this case, so the Hilbert space decomposes to the Q sector. So is this Hamiltonian? So do you have? Can you write in this way uniformly? So doesn't it depend on the sector?
So the choice of sectors are automatically done if we
sorry. So this Hamiltonian is acting on this total Hilbert space.
Yes, right.
I see.
Right. And change the value of theta or mass or then some lowest sector is selected by the simulation.
I see. Yeah, thank you.
So any more questions? Yes, if not, let the sun speak again.